So what I would like to talk today is about applications of topology to physics and applications of physics to topology. And probably right now it is right time to list these developments and to say that in 50 years, starting 74, really there was a revolution in relation of mathematics to physics, and in particular a revolution of relations of topology to physics. 50 years ago, more or less, there were no physicists that knew basic notions of topology. Today, the situation is completely opposite. If you compare knowledge of topology of mathematicians, of average mathematicians, and average physicists that works in quantum field theory, you will see that every person that works in quantum field theory or in string theory should know some topology, and only a small fraction of mathematicians know topology better than physicists, than average physicists. And the situation is really very clear here. So you can work in mathematics really in fields where topology is not important. It is important in many branches of mathematics, but not in all of them. At the same time, physicists working in quantum field theory should know some basic notion of topology, because they are important in some basic questions. So the applications of topology to physics starts with notion of topological quantum numbers. And this notion led to the notion of topologically non-trivial solutions of equations of motion. These solutions, this stability of these solutions is guaranteed by topological considerations. Among these topologically non-trivial solutions are magnetic monopoles, and I will talk a little bit about them. But there are also topological non-trivial defects in condensed matter theory. Really, the understanding of them came from analogy with quantum field theory. There are topological defects that are point-like, or the best example is magnetic monopole, or string-like. I will talk about something called Ellis strings. But also you can work in Euclidean formulation of quantum field theory. And then you get a notion of instanton. I will talk also about the notion of index of an operator. Now, although everything in this list is well known in the community of physics. Another thing that I will talk about is applications of physics to topology. Really, physical considerations led to the notion of topological quantum field theories. And this is really a very important notion. It is important to mathematics because it gives new topological invariants, but also invariants of a different kind. Again, here the most important thing is Chern-Simons theory that led to new invariants of nodes. But this is about applications of physics to topology. But topological quantum field theory plays a very important role in physics also. Not only there is a viewpoint that topological quantum field theory should be useful, first of all, for mathematicians. And this is wrong. It is equally important for physicists. And I will say only one thing about this right now. Namely, I would like to mention that if you work in string theory, then what is called a target space of string is a topological quantum field theory. So this, right now I gave some list of things that I will mention. But let me give some more details. First of all, one important idea, a very simple one, that phase space can be disconnected. What does it mean? So really, you have phase space. This is a symplectic manifold in mathematical terms. It can be, it can consist of some fields or what else. And this phase space can be disconnected, which means that you cannot go from one point of this space to another point by continuous curve. And this leads to a notion of topological integrals of motion. This notion really appeared in works by Chern, by Finkelstein and Rubinstein in the 60s. So it led to the notion of skyrmion, which is topologically non-trivial field in sigma model. I would like to remind to you that sigma model is a model where you have fields that take value some manifold that in general can be nonlinear. So in mathematical language, you consider some maps of your original space to another space. So, and this is something that considered in topology. When you consider two spaces, two manifolds, you consider the set of all the maps from first manifold to the second one. In the space of continuous map of this kind can be disconnected. For example, if you consider two spheres, then two spheres of the same dimension, say of dimension n, then you have a characteristic of a map of one sphere to another sphere, which is called degree. Degree is the number of times that the first sphere covers the second sphere. Or you can say this in different words. You can consider a map of one sphere to another sphere of the same dimension, and you consider pre-images of a point in the second sphere. So this in other words, you consider solutions of equation f of x equal to y, where y is a point of the second sphere. And you consider the number of solutions of equations f of x equal to y. Of course, this number of solutions can depend on the choice of y. But the wonderful thing is that you can talk about algebraic number of solutions of this equation. And the algebraic number of solutions then doesn't depend on y. And it is by definition of the degree of the map. I will not give precise definitions now. This is not a lecture about topology. This is a lecture about history of application of topology to physics and vice versa. But this paper by Chern and other people were unnoticed for a long time. And the real revolution came with invention of magnetic monopoles by Polyakov and Hooft in 1934. So the precursor of this stuff was magnetic monopole by Dirac. But magnetic monopole by Dirac was a singular solution of equation. What Polyakov and Hooft understood is that if you have gauge theory, which is corresponds to non-commutative group, with non-commutative gauge group, then you can construct smooth magnetic monopoles, smooth solutions, smooth fields that have non-trivial magnetic charge. This magnetic charge can be obtained as an integral of magnetic field strength over some sphere. And when you are working with electrodynamics, which is gauge theory of with a billion gauge group, then you have zero as this integral by Stokes theorem. But in the case when you are working with non-commutative gauge group, say with group SU2, you can find that you have very well-defined field is smooth magnetic and electric fields. But in this case, when you construct, you can still construct magnetic charge, which case you can construct magnetic field strength, but you can this magnetic field strength will not be continuous, even if the field itself is continuous, and therefore you can have magnetic monopoles. This magnetic monopoles can be interpreted as solitons, and in general, all this stuff is related strongly to solitons and generalized solitons that can be characterized as particle-like solutions of classical equations. But what were discovered at this time is that for every stable particle-like solution of classical equation, you can construct a quantum particle after quantization of particle-like, stable particle-like solution, you get a quantum particle. And this is really a very interesting phenomenon, because it gives you non-perturbative information about particle content of a quantum theory. So I will talk about my papers written with collaboration with my students, Tupkin and Faseev. where all this stuff was analyzed not only for SU2, as was done in papers by Polyakov and Hoft, but also for any other gauge theory. And this was also found at the same time by Monastyrsky and Perelomov. So what was described in my paper, the paper with Shubkin and Atiyah in 1975, under the title Heavy Particle in Gauge Theories. What was found there and later developed in my paper in 1976. So look, what happens in gauge theories? In gauge theory, you have gauge fields, but also other fields that are Fermi fields or Bose fields. In particular, you can have scalar fields since scalar fields come with some potential. What you should do to find particles corresponding that appear in your gauge theory, you should look at ground states and elementary excitations of this ground state. But how to find this ground state? Okay, first of all, you should work in classical way. When you work classically, then the ground state corresponds to minimum of this function that appears in scalar fields, the functions of scalar fields. So that function has several minima. Moreover, this is more or less standard situation. Why? Because you have a gauge group. Let us suppose that the gauge group is denoted by G. And so that's when you have some minimum of energy of scalar field, then acting by G, you will get another minimum. So basically, if you say that classical vacuum is the minimum of energy of scalar field, then the group G acts on the set of classical vector that I denoted by R. So this group G, the action of group G, it creates the generation of classical vacuums. You have a set of them, not only one. And you really can say that the standard situation is when G can transform any classical vacuum to any other classical vacuum. Mathematicians say that G, it is reasonable to assume that G acts on the set of classical vacua transitively. You have transitive action of group G. So it is well known that in this situation you can consider R as a quotient of G with respect to some subgroup that I denoted by H. And so this is a group of unbroken symmetries, really, because G transforms one vacuum to another vacuum. This means that the vacuum is not symmetric with respect to all transformations of the group G, but it is symmetric with respect to a part of it. So general element of the group G is a symmetry, but a symmetry, this is a symmetry of the theory, but not the symmetry of vacuum. And so you see that some transformations of group G are unbroken symmetries, and some of them are broken. And you can say that the set of R is a quotient space of R with respect to this group H of unbroken symmetries. Now, you can say that you can say that your fields, they form a disconnected set. Really, look what happens. At infinity, you definitely, your field should be close to classical vacuum if it has finite energy. Otherwise, the energy will be divergent. So you see that at infinity, you will have a map of the stuff that is far enough to R, to the set of classical vacuum. But the set which is far enough, it contains a two-dimensional sphere. Our space is three-dimensional, and so that's at infinity you have a two-dimensional sphere, and so you have a map of two-dimensional sphere to the set of classical vacua, to R. But this is a mathematical object that you topologists know very well. When you have this mathematical maps of sphere to some space, then in general, the space of maps is a disconnected infinite-dimensional manifold. And if R is simply connected, then the point of this space are labeled by elements of what is called homotopy group. If you have two-dimensional sphere mapping to R, then you have two-dimensional homotopy group. So really, these elements of this group should be considered as topological topological numbers. So it is a mathematical problem to calculate this group. This was done in our paper. You can prove that two-dimensional homotopy group of the space of R is equal to one-dimensional topological, one-dimensional homotopy group of H, of the group of unbroken symmetries. And this is very easy to calculate, this group. So it's really H itself, it contains some, not, you can consider the case when G is a compact gauge group. So H also will be compact, and it can be represented as a direct product of non-abelian groups and abelian groups. This pi one-dimensional homotopy group comes from abelian groups. And so this simply, you can say that pi one will be free abelian group, and the number of generator of it is equal to dimension of abelian direct summand of the Lie group. For example, if you take G equal to SU2, then the situation of Polyakov and D'Hooft, H is simply U1, and you have one topological quantum number. And so you have say if you have H equal to SU2, not G, but H equal to SU2, then SU2 is U1 locally is U1 multiplied by SU2. If H is U2, unitary group of two dimension, then you have one-dimensional abelian summand, and again you have one topological quantum number. And later, this topological quantum number was identified with magnetic charge. This was done in my paper written in 1976. This is was really a very important discovery because it's predicted that there are magnetic monopoles in any gauge theory that has simply connected compact gauge group. In particular, if you have grand unification theory, then precisely in grand unification theory, you assume that the gauge group is simply connected, or at least has finite fundamental group, finite by one. And then, if you believe in grand unification theory, and probably most physicists believe that strong, weak, and electromagnetic interaction should be unified in such a theory, then you should believe that there are magnetic monopoles, but you cannot find them. There are no experiments that give you any hint on existence of magnetic monopoles. So you should explain why these magnetic monopoles do not exist, at least if they do not exist, you should explain why they are not found yet. And one of this was one of the sources of what is called inflation cosmology. This where people think that there was some period of time when our universe expanded rapidly. And if you believe in this inflation cosmology, you can explain why you do not see magnetic monopoles. As I said, that this discovery of topologically non-trivial particles in gauge theory led to discovery of topological defects in solid-state physics. And the first paper in this direction was written by Volovik and Mineev. But later, it was understood that topological defects in solid-state physics are very common. That you can have point-like and string-like defects. So this is, again, the classification of these defects is precisely the classification in terms of homotopic groups that appears in gauge theories. Later, there were many papers that were considered the solitons and generalized solitons as examples of topological non-trivial solutions that have non-trivial topological quantum numbers. But what I would like to explain now is that really, even when you have topologically trivial solitons, this is also a very important thing. And maybe I would like to say about one of my papers of more or less of the same time, where it's also written in collaboration with Atiyah-Singer, that is called, this paper is titled Classical Limit of Quantum Scattering Matrix. And this is a paper about relation between quantum particles and classical particle-like solutions. What I would like to, I believe that one of the conjectures which was made of this in this paper, which is still is not proven, but I believe it is really important. And this conjecture is as follows, that when you consider any theory that has solitons, first of all, if you consider any theory that has no solitons or generalized solitons, then generally you have the following picture. Then for small values of amplitudes, you have a nonlinear equation, but nonlinearity can be neglected when the amplitude is small. And so, and therefore, you should expect that every solution, when time tends to plus infinity, can be approximated as a solution of linear equation. And this is, in some cases, mathematicians have proven this conjecture. It was done before our paper was published. But the conjecture of this paper is that in general, when you consider a general nonlinear equation, which is translation invariant, then at the end, you will get some solitons or generalized solitons, which are accompanied by some stuff that approximately satisfies linear equation. So this conjecture was later, similar conjectures were later made by mathematicians. It's called by Grand conjecture by Seufer, and soliton resolution conjecture by Tau. And I believe that it is not proven yet, and nobody knows any way to prove it. But I believe that it's important for understanding not only classical theory, but also quantum theory. So I was talking now about topology magnetic monopoles, which are topologically stable point-like solutions. There are topologically stable string-like solutions. And in the gauge series, they are classified by one-dimensional fundamental group of space of classical vacua that I denoted by R. And so that's, or you can prove that they are classified by elements of connected component of the group of unbroken symmetries. So I have written a paper, really several papers, with analyzing this situation. And one of them is called series with non-local conservation of electric charge. So it seems that this topologically non-trivial string-like solutions, they can play an important role in cosmology. Now, the standard gradual unification series, they really have connected group of unbroken symmetries, connected group H. And so they are not predicting this topologically non-trivial string-like solutions. However, there is some gradual unification series that do predict the existence of such solutions. And really, such series were constructed in my paper with Stupkin in 1982. And this series, they are based on the idea that you have what is called mirror particles. So you know that in that theory, that the symmetry corresponding to mirror reflection, denoted by P. This is space-time symmetry, is broken in quantum field theory that we consider. It is broken in standard model. However, there exists a conjecture that people do not, that it is not broken. It's really this. It's very unnatural to think that left and right are not equivalent. But we right now we really believe that they are not equivalent. But probably this is not a very natural thing. And people think that maybe there is this space-time symmetry is not broken, really. Simply, space-time reflection, it transforms the particle that we know, and the particle that we do not know, that are called mirror particles. And we do not know these mirror particles simply because they interact very weakly with the particles that we know. So that's this is the conjecture that there is there is this gradual unification theory which has mirror particles. However, then the group, the symmetry group of the theory should be disconnected. And as I have said, that really this means that you have topologically stable string-like fields. And I call them Alice strings. Alice is the same Alice that in Lewis Carroll books where you see that there is a similarity with Alice traveling through the looking glass, and you're traveling to mirror particles, to the world of mirror particles. But how Alice could travel to this world? And the situation is very, very interesting. Really, what I discovered is that if you have topologically non-trivial string-like field, then going around this field, a particle changes its style. It goes to the particle of different type. In particular, if you have this H as reflection symmetry, then going to non-trivial around string-like field, you your particle becomes a mirror particle. This is the reason why I call this string-like solutions Alice strings, because Alice could go through the looking glass simply going around this Alice string. This is a very unusual situation that I really, when I really found it, I thought that there is a very good idea for some fantasy book based on the existence of Alice strings. But of course, I did not write such a book, but somebody did. And so that's what what you see on this slide. You see that there is a book that you can buy on Amazon, which is called the Ellis encounter. So in this book, this mirror matter is identified with dark matter. So you know that we know now that there is a dark matter that we cannot see. So if you have mirror particles, then you can really think that the dark matter consists of the mirror particles. And then, so that's Ellis matter. I'm reading from a description of this book. Ellis matter can be turned into ordinary matter and vice versa by sending it through a loop of Ellis string, an naturally occurring cosmic phenomenon. Yeah, this Ellis strings, they're in principle, they can be observed. If there exists, so of course you cannot see any string, but if any string is moving and its trajectory covers some star on the way, then you will see the star consisting of mirror matter. So basically, if you have some abrupt changes in the behavior of a star, it can be explained by Ellis strings coming on the way of our of light from the star to us. Yeah, people try to find phenomena of this kind that really, yeah, there are some stars that is abrupt changes in their behavior. This can be explained in terms of Ellis strings. However, the problem is that there are other more complicated but less fantastic explanations. Also, I would like to say that I discovered that in series having Ellis strings, you have non-conservation of electric charge, but it is a non-local conservation, which means that you cannot, you have electric charge, you can calculate the electric charge integrating something. However, this conservation is not local. This charge is not localized. So some people invented a very nice name for such non-localized charge. They call this Cheshire charge. Again, from there is Cheshire cat in Carroll's book, where this cat disappeared, and what remains only his smile. Okay, but this is precisely what happens with non-local conservation of electric charge. So there are not only L strings, but also you have Cheshire charge. So now I talked about topologically non-trivial solutions of equations of motion, which have some where you have this topology that guarantees the stability of these solutions. But also, what do you have? You have also the possibility to consider topologically non-trivial extremal point of Euclidean action. This, so you write your equations in four-dimensional space. And these topological non-trivial extremal points of Euclidean action are called instantons. If you consider extremal points of Euclidean action of gauge theory, then you can get gauge instantons. And these gauge instantons were discovered in the paper I have written in collaboration with Belavin, Polyakov, and Tubkin. It was found that there is a number, topological number. A topological number can be characterized as Pontryagin characteristic class of field. And there are equations satisfied by field strengths of self-dual and anti-self-dual gauge fields, which so this is this equation for non-trivial extremal point of Euclidean action. This is, you have what is called operation Hoch-Star, and you consider F as two form. These equations of for extremal point of gauge action is F is equal to star F up to a sign. So this gauge instantons, they are associated with tunnel transitions. And so they were called pseudo-particles in our paper, but later at Hooft suggested the name instanton for them, and not only the name, he found so many interesting properties of instantons. For topological number one, there is a very explicit solution which in some sense has spherical symmetry. In some sense, because the solution doesn't have spherical symmetry. However, if you have rotation, then the field goes to gauge equivalent field. You have rotation invariance up to gauge transformations. And this is allows you to find the solutions, and many other solutions of this find also can be found. But these solutions are not all solutions. And really, it was discovered that there exists a space of instanton which is multidimensional. For example, in the case when the group is equal to SU2, the gauge group is SU2, and then is a topological number, the dimension of the space of instantons is equal to 8n minus 3. So this is really a very important statement. Even more important was the way how it was discovered. So really, this is this was discovered by using what is called Atiyah-Singer index theorem. And this was the first use of this theorem in physics. And later, this theorem and generalization of it by Witten were very instrumental in many problems of quantum field theory and statistical physics. So really, what this theorem it says to you is for some class of operator that are in a sense close to invertible, but not invertible. They are called Fredholm operator, and they can be represented as invertible operator plus operator of which is compact or finite or have finite dimensional image. So this is Fredholm operators, and for these Fredholm operators, you can calculate index of this operator, which is dimensional of the kernel of this operator, number of kernel that number is the set of zero modes in mathematical definitions. So here you take zero modes, number of zero modes of A, minus the number of zero modes of Hermitian conjugate operator. And then the difference between these numbers is called index. And it has wonderful property that it does not change when you change the Fredholm operator continuously. And this allows you to calculate this index. But there is a more a better way to calculate, which is based on Atiyah-Singer index theorem, where this index is represented in terms of other topological invariants. So it was used in my paper to calculate the number, the dimensional space of instantons. However, this is as I said, this theorem can be applied in many other situations. And in particular, I used it to calculate the number of zero modes of Dirac operator in the field of instanton. So this again, this number of these zero modes is related with what is called Adler-Bell-Jackiw anomaly. But I cannot talk about this in more detail. There was a paper by Atiyah-Singer that generalized the stuff that was done in my paper for SU2. It was generalized for general gauge groups. Then there was a paper by Atiyah, and Manin, this ADHM construction, that is more or less explicit construction of all solutions of self-duality equations of all instantons. So there were many papers. When I looked recently, the number of citation of this paper, now this number of citation is more than 4,000. And really, I think that there are many papers containing the word instanton without the reference of this paper, because it is well known, and all of this stuff doesn't deserve any reference anymore. Probably I have some time to say a couple of words how this paper for people was written. So really, this is an example of the role of chance in history. So really, there was a conference in Taganrog. This is south of Russia. It is as a small town on the coast of Azov Sea, and both I and Polyakov and Stupkin participated in a workshop in this Taganrog, and I met Polyakov already on the way to Taganrog. By chance, we traveled in the same carriage, and we started to discuss physics at the very moment the trains started to go to Taganrog. And this is a long way. This probably about 8 hours or so. And then we continued the discussion on this Azov Sea. And it was very hot, but it was really the one way to get a good discussion was to go to the sea and discuss the stuff in the water. Later, on the train back, I was together with Shubkin, and we continued to work on this stuff. And later, already in Moscow, Belavin joined us. So this was a short history of the appearance of this paper. What I would like to say now that this paper is important not only for physics, but also in mathematics, in particular in the paper by Donaldson, that it was used to classify four-dimensional smooth manifolds. This was the paper of Donaldson that gave him Field's medal. So, but now I have some time to talk about topological field theories. And this is this series came from the first example of the series came from my attempts to understand topological invariant, or better to say invariant of smooth manifold, called Atiyah-Singer torsion. Atiyah-Singer torsion, in a sense, this is a smooth version of something called Rademacher torsion. And this Atiyah-Singer torsion was defined as some combination of determinant of Laplace operator on differential form on smooth compact manifolds. And I wanted to understand how to construct this invariant from physical viewpoint. And I came to the notion of topological quantum field series. When the series are defined on smooth manifold, but the action functional doesn't depend on Riemannian metric. Now this is called topological quantum series of Schwarz type. And the simplest example are fields, this situation where you have differential n forms on two one-dimensional, two n plus one dimensional smooth manifold. And this, you have the integral of alpha, which is n form, multiplied by d alpha, where d is the differential, the RAM differential, which doesn't depend on Riemannian metric. So this integral is considered section functional, but it doesn't depend on Riemannian metric. But if you would like to calculate something with this action functional, you should take into account that you have gauge invariance, and you need Riemannian metric or something else to impose gauge conditions. But physical quantities do not depend on choice of gauge condition of Riemannian metric, and so they should be invariant of smooth manifold. But this is the main idea. that is sufficient to consider three-dimensional manifold n equal to 1. However, when you have n is greater than 1, then you have gauge transformation are degenerate in its own right, and you have to fight with this additional degeneracy. But I've developed some methods to deal with this stuff, and this led precisely to Atiyah-Singer torsion. Okay, so that's this was the very beginning, first examples of topological series. However, it was an interesting development later. Namely, at some moment, Turaev, Russian mathematician, came to me to explain that Atiyah-Singer torsion, Rademacher torsion, is related to Alexander polynomial of knots. But Jones invented a non-commutative analog of Alexander polynomial. And so Turaev asked me, so Alexander polynomial can be explained from the viewpoint of physics? And so maybe Jones polynomial can be explained. And I really came to the conjecture that yes, there is a theory which is called Chern-Simons theory with action functional written here, which is now very, very well known. This is a non-commutative, this can be defined for any compact Lie group. And this action functional should lead topological invariants. But I made the natural conjecture that when you can work with nodes, it leads to Jones polynomials. I was not able to prove this conjecture. However, a year later, independently, Witten came to the same conjecture, but Witten have proved it. Really, this wasn't a proof from the viewpoint of mathematician, but really very good proof from the viewpoint of physicists that really Chern-Simons leads to Jones polynomials. So this was the beginning of topological quantum series. First examples of them, and really the development of this topological series is subject of work of many physicists and mathematicians. I cannot talk about all these achievements. Probably the only thing that I would like to mention is that Witten invented also a new type of topological quantum field series. I considered really action functionals that do not depend on metric at all. Witten allowed the dependence of metric. However, he did not, he required that this dependence of metric is in some sense trivial. It is what is called BRST trivial. There exists a method to work with physical series, introducing some additional fields. But you are introduce some additional fields, but you are paying for this introduction by some nilpotent symmetry. In mathematical language, this corresponds to what is called homological algebra and free resolution of module. So Witten is suggested to introduce topological series where dependence on metric does exist, but it is BRC trivial. And this led to many new examples of topological series. In particular, topological series which are related to mirror symmetry. So I don't think that I have any time to describe all these important developments. So and I think that this is not the end of application of topology to physics and physics to topology. It's only the very beginning, but definitely this is the end of my today talk. Let me finish at this point.
Professor Schwarz, thank you very much. Does anyone have any questions?
Yeah, I have a question, if it's all right for me to go first. Professor Schwarz, first, I just want to thank you for your talk. So my question is, given your influential contributions to both mathematics and physics at a time when the boundaries between these fields were shifting, looking back, do you see yourself more as a theoretical physicist or a mathematical physicist? And as a slight follow-up, how did the evolving relationship between these fields influence your research?
So first of all, I would say that I learned from Wikipedia that I am a mathematician and theoretical physicist. I hope that this is true. What I do not consider myself, I don't consider myself mathematical physicist, because in some sense, people think that mathematical physics is an attempt to make rigorous the stuff that physicists believe but do not know how to prove rigorously. So that's this is not my direction. At some moment, nuclear physics had a definition of physical mathematics. Physical mathematics, from the viewpoint of Journal of Nuclear Physics, is such mathematics that has some applications to physics, that solves some physical problems. So if I consider myself, if I should characterize myself in one word, two words really, then I consider myself as a physical mathematician. My field is physical mathematics.
Thank you very much for the response.
Professor Schwarz, thank you for your talk. So you came into physics as a mathematician, and you also mentioned that topology was introduced into physics by Toft and Polyakov. I was wondering if you could say something about how much mathematics that physicists were, did they know a lot of topology at the time? And for example, Polyakov and Witten say that they had never heard of the Atiyah-Singer index theorem. So was the connection between the fermion modes and the Atiyah-Singer theorem obvious to you? So I was just trying to get sort of a characterization of, at the time, how were these things viewed? How was mathematics and topology viewed by physicists, and how was it viewed by you? Was it like obvious to you, or was it something that you thought you had to learn a lot of physics for, so on and so forth?
So I would like to say that, of course, it helped that I was a mathematician and I was a topologist, and so I knew some stuff that physicists did not know. But they learned very fast. So that's, I think that one of my roles was to be a person that connects mathematics and physics. And so that's, in a sense, I think that this is one of my contributions. I hope not the most important, but I think that's really important.
Was it your idea to consider the extrema of the Euclidean action in instantons?
Sorry?
Was it your idea to consider the extrema of the Euclidean action in your work on instantons?
No, this was idea of Polyakov, and it was, moreover, he considered this, he applied this to three-dimensional series before that. This idea, this was his idea, not mine.
Okay, thank you.
Okay.
Are there any other questions?
Yes, thank you very much, Dr. Schwarz, for the presentation. It was very enlightening and a wonderful opportunity to see some of your work presented in such a fashion. I have a question with regards to your personal interests in invariants in topological quantum field theory. What was your initial motivation coming from the point of view of mathematics and topology to seek a invariant path integral formulation in physics?
So really, I was inspired by physical questions, so that's I try to answer these questions, and so that's this is one of things that he always trying to do. So it's difficult to answer this question. So I really cannot explain. Nobody can explain precisely how to get his results. This is a complicated thing.
As a follow-up, how do you feel about the effectiveness of your formulation of topological invariants, specifically the work that's been done in Chern-Simons theory with regards to adding the notion of knot-based invariants to topological quantum matter?
Sorry.
It's really a question about the effectiveness of the approach of topological invariants in field theory.
So so what can I say? The history shows that the topological methods are really very, very efficient in many situations. So this is, but this is not something that I can explain. This is this effect of history. Of course, I was very happy when I discovered that I can apply physics to topology. This was, I gave several talks, first about applications of topology to physics, and then about applications of physics to topology. I was very happy that I was able to find this connection. But I am very happy with the stuff that happened later already without me, with my participation, but mostly with other people results. So right now there is a really very, very complicated and interesting mathematical theory of topological quantum field theories. There are papers by Lurie where he analyzed what is called extended topological theories very carefully, and these are papers that are definitely very important. However, even for me, and I am a mathematician by origin, they are difficult. From the other side, there are many applications of topological quantum field theory to pure physics, and that's also. So that it was discovered that this topological quantum fields, if you have a supersymmetric theory with n equal to supersymmetry, then you can construct topological theory that permits you to solve a big chunk of n equal to supersymmetric theories. So what I can say only that I am very happy that there are many, many directions where all the stuff was developed, and I'm also happy that I did many things outside of this topological business. So.
Thank you very much, Dr. Schwarz. It's truly an honor to speak with you. Your work has been very informative of my own. So personally, this has been a great experience for me. So thank you very much for speaking with us today.
Thank you for your attention. It is also very nice for me to remember all the things and to give you, to explain to you some pieces of history. So, thanks, bye.
Oh, are we still taking questions?
Oh yeah, go ahead.
Oh,
So you're,
Uh,
yeah, are there any other questions? Yeah.
oh, I have a bit of a follow-up on a previous question. So, first of all, thank you very much. It's an honor to be here, and thank you very much for an insightful talk. And I wanted to ask about the 10-year gap between your 1978 work on TQFT and then Witten's work on TQFT, and then later Turayev and it kind of returning to low-dimensional topology. Could you say something what you were thinking about TQFT at that time in between?
About what? About what?
About the topological quantum field theory.
About the quantum field series. So really, I don't know if, so first of all, so what can I say? This is topological quantum field theory is really something that covers a lot of very, very different things, which was done with these very different perspectives in mathematics that led to it was studied in the framework of category theory. And I believe that really not very many physicists can understand these viewpoints. But now physicists, there are physicists that really know much more mathematics than mathematicians do. And this is really a very nice thing when really right now what happened that you have a large field which is between mathematics and physics. And so you have string theory that many people believe that physics comes from strings, so that I do not know whether string theory is physics. And there are many people that do not know whether string theory will become physics. But what I am sure that maybe string theory will not become physics, but still there is a lot, it is a part of science that is not physics yet, but it has a chance to become physics. And I believe that what I did is a large part of it is physics already, but a large part of it has a chance to become physics. And so that's the existence of this gray area between mathematics and physics is for many people that consider themselves as real physicists. The existence of this gray area from their viewpoint is bad. So that's physics should be related to the real world, they think. And they, in a sense, they are correct. But anyway, there is a lot of achievements that definitely should be considered as good science. Nobody can say that string theory is not a science. It is. Maybe this is not maybe this is not physics, but still this is, I believe this is an important part of science. And I believe that the existence of this gray area is good, not bad.
Thank you very much.
Okay, I think we're going to end the talk here. Thank you very much once again, Professor Schwarz.
Okay, thank you.
Thank you again.